All right, let's get you ready for your GCSE chemistry exam. We're going to break down everything you need to know about the rate of reaction, focusing specifically on that AQA 4.6.1 spec.
So here's our game plan. We'll start with the absolute basics, what reaction rate even is. Then we'll dive into how you actually measure it, what things can speed it up or slow it down, the theory that explains all of this, and finally, we'll look at catalysts, which are kind of like a chemical cheat code.
Okay, first things first, what do we actually mean when we say the rate of a reaction? It's the bedrock of this whole topic, so let's make sure we've got it locked down. Put simply, it's just how fast a reaction happens. It's a bit like a car's speed. That's just distance over time, right? Well, in chemistry, it's how much stuff you use up, or how much new stuff you make, over a certain amount of time. And it's not enough to just say, oh, that was fast. We need to put a number on it. For your exam, you absolutely have to know two key formulas that let us calculate the mean or average rate of a reaction. So you've got two ways to look at this. You can either track how quickly one of your ingredients, the reactants, is disappearing, or you can track how quickly your final product is appearing. The units you use totally depend on what you're measuring. If you're weighing a solid product, for instance, your rate might be in grams per second. If you're collecting a gas, it'll probably be in centimeters cubed per second.
Okay, so we've got the formulas, but how does this actually look? This brings us to a massive skill for your exam: reading and understanding reaction graphs. They love asking questions about these, so let's pay close attention here. So a classic reaction graph looks just like this. See how it starts off super steep? That's where the reaction is at its fastest, because you've got loads of reactants ready to go. Then, as those reactants get used up, the reaction slows down and the curve gets shallower, and eventually, it goes completely flat. Now, why is that? Well, it's because the reaction has stopped. One of the reactants has completely run out. But what if the examiner throws you a curveball? What if they don't want the average rate, but the rate at one single specific moment? Let's say exactly at 30 seconds. Our mean rate formulas won't work for that. We need a different trick up our sleeve.
Here's what you do. To find the rate at a specific point, you draw a tangent. Now, a tangent is just a straight line that perfectly kisses the curve at that one point. Once you've drawn that straight line, all you do is calculate its gradient, the change in y divided by the change in x. And believe it or not, that gradient is the rate of the reaction at that exact instant. And a quick heads up for all you higher tier students, this is a big one for you. It's not optional. You won't just describe how to do it. You'll actually be given a graph in the exam, and you will have to draw that tangent and calculate the number to get the marks.
Right, so we know how to measure the speed, but how do we change it? How can we control it? Think of these as the 5 main control knobs you can turn to tweak the speed of a reaction.
For your exam, you need to have these 5 factors memorized, no question. They are concentration or pressure if you're dealing with gases, the surface area of your solids, the temperature, and finally, whether or not you're using a catalyst.
But why? Why do these things actually change the speed? The answer to everything lies in a really important idea called collision theory. If you get this, you get the whole topic. It's actually a pretty simple idea, but it's super powerful. It says that for a reaction to even happen, 2 things have to be true. First, the particles have to physically smash into each other. And second, when they do collide, they have to hit each other with enough energy. There's a minimum energy required, and we call that the activation energy. So let's connect this to our factors. If you increase the concentration, you're basically just cramming more particles into the same amount of space. What's going to happen? Well, they're going to bump into each other way more often. That means more frequent successful collisions, and more successful collisions per second means a faster reaction. Simple as that. It's the exact same idea for increasing the pressure of gases. Now, cranking up the temperature, that's a real double whammy. It's a 2-for-1 deal. First, the particles get more kinetic energy, so they start whizzing around faster, which means they collide more often. But, and this is the crucial part, they also collide with way more energy. So a much bigger percentage of those collisions will actually have enough energy to be successful. The rate just skyrockets. And what about solids? Well, it's all about surface area. Imagine a big sugar cube. Only the particles on the very outside of that cube can react. But what if you crush that cube into a fine powder? Suddenly, you've exposed all those particles that were hiding on the inside. You've massively increased the surface area, which means more particles are available to collide, and the reaction speeds up. Which brings us to our last factor, the catalyst. And this one is clever. It works in a completely different way to the others.
So a catalyst is this amazing substance that speeds up a reaction, but here's the cool part. It doesn't get used up itself. It's like a chemical matchmaker. It helps the reactants get together, but it doesn't become part of the final product. It's still there at the end, totally unchanged. And we can actually see how a catalyst works by looking at something called a reaction profile diagram. See that big orange hump in the middle? That's the activation energy, that huge energy barrier that the particles have to get over. What a catalyst does is it basically lowers that hump, creating an easier path, like the blue line here. Now, this quote right here from the AQA spec itself is the golden phrase you need to remember. This is what you write in the exam. A catalyst provides a different pathway for the reaction, one that has a lower activation energy. It's like finding a tunnel that goes through a mountain instead of having to waste all that energy climbing over the top. And there you have it. That's your complete guide to the rate of reaction. We've defined it, we've measured it, and we've used collision theory to explain the 5 big factors that control it. The real test now, though, is for you to take all this theory and actually apply it. Go on, find a past paper question and see if you can put it all into practice. You've got this. Good luck.